Welcome back. In the previous lecture, we talked about the different types of interaction forces or intermolecular interaction forces. As we told that in this particular lecture and probably in the subsequent one, we will continue talking about these interaction forces between two charge neutral apolar surfaces. So, we get started with the fact that the potential energy of interaction between two molecules or atoms due to induced dipole type or the dispersion force type van der Waals forces is given as x is sort of you can regard as the separation distance between the centers, and therefore, one has to understand that when these two molecules or atoms come in direct contact, x will not be 0, because of the fact that if they are the separation distance between the centers. So, as they come closer, their electron clouds first sort of start overlapping. Which gives rise to short range repulsion, which is also known as the bond repulsion. And this essentially we understand this corresponds to this part of the curve, because had there been no repulsive component at x tending to 0, following this relation, the interaction would have tend to minus infinity, which does not happen. So, we also consider stiff bond repulsion at very close proximity, which is due to direct overlap of electron cloud, or also this is also sometimes referred to as the so called hard sphere model. Anyway, so phi dash r, the repulsive component of the potential energy, one can write as, let us say we use the prefactor L x to the power beta. So, therefore, the pairwise potential, or as we will be referring as pair potential between two atoms is given as L. We use the term phi dash. So, let us try to understand this is the pairwise potential energy of interaction. So, this is the pairwise potential energy of interaction between two molecules or atoms, and whether the atoms or the molecules are of the same species or they are of the different species, even if they are of the same species, but depending on species to species how the properties of individual atoms, individual molecules, their molecular radii come in, that comes in through these two constant beta and L. So, these are material specific constants. However, the generic nature of interaction remains unaltered irrespective of the exact system. Okay. So, that is important. So, let me just again repeat. So, this is the pairwise potential energy of interaction between two atoms or molecules, and this refers to the van der Waals attraction, and this refers to the short range bond repulsion. Now, we will be interested to look at the interaction, the potential energy of interaction between two blocks let us say 1 and 2 with which has thicknesses d1 and d2 and d1 and d2 respectively, and are separated by a distance d. So, this is very simple. So, you have a block, this is block 2, this is block 1. The thickness of this block is d2, the thickness of this block is d1, and these two blocks are separated by a distance d. We are interested to find out the total potential energy of interaction between these two blocks, and for that we will be assuming only the attractive, or we will consider only the attractive part of the van der Waals interaction. So, we will be considering this with the fact that these two blocks, the nearest they can come is when they come in contact, but in that case we will assume that d is not going to be equal to 0, but it will be some d0 which essentially corresponds to this point. Okay. So, this point is the minimum distance at which it can come. So, since it cannot come to a distance below this, let us say d0 or xm or whatever, therefore, there is these two blocks can never be subject to the repulsive interaction, and it is perfectly justified to consider these attractive interaction only. Okay. So, one can also from this particular relation, I just forgot to mention, one can from this particular relation one can set del phi del x is equal to, or del phi dash del x is equal to 0 to obtain a value of x m which turns out to be equal to 2L by beta raised to the power 1/6. So, this gives you the minimum in the potential curve, and from that you can find out the minimum distance where the two atoms or molecules can sort of come in contact. So, this d0 we consider is essentially an equivalent of that between two surfaces. So, this is, let us point it out, minimum separation distance between two surfaces. Okay. So, now in order to find out the interaction between these two blocks, what we do is we consider a single molecule of 2 located at a distance z from the surface of block 1. So, let us say this is one molecule which we consider, and this distance is z. Okay. Now, we identify a location, let us say, which is at a distance zeta away from the top surface. It is inside the block, and we consider a annular ring over here, a thin ring. Of width del zeta. If you follow the construction, you should be able to understand it very clearly. So, this is dz, this is y, and let us say the width of the rim is del y. Okay. So, this is the thickness of the rim, this is del z, and let us say this is the width of the rim. Sorry for the slightly poor construction. This is del y. So, this is dy, this is dz, this is a annular ring which we have considered. This is the center. The center is at a distance zeta away from the surface, the width is dz, this is the thickness is del y, and this is y. Okay. We will be eventually doing a construction later. So, I will just attach it, this line, and this we mark as the distance as x. Okay. Now, I will repeat, we have picked up one molecule of material 2, and we have identified a zone of this nature, an annular ring. The center of this ring is over here, which is at a distance eta from the center from the top surface of block 1, and the point or the particle which we have identified is at a distance z from the top surface of block 1. So, this particle can lie within the limits of z equal to d to z equal to d plus d2. That is the bounds over which the particle can lie. So, this is z equal to d, the particle can be here or at any location down all the way up to here. So, this is d to d plus d2. For the particle, for material 1, we have identified an annular volume like this. Okay. Now, the volume of this ring like thing, you have to keep this in your mind for a while, or maybe we will have a quick smaller version of the picture over here. So, this is the location, this is z, this is eta, this is delta eta, this is y, this is delta y, and this you join up to get x. So, this is the sort of the shortened version of the picture, which we will carry in our subsequent slides. When in a classroom I teach this thing, I typically have this picture in one corner of a big blackboard, but that much amount of leverage you have to give me in a video lecture. So, I guess this picture you once again have a detailed look. So, two blocks of width or thickness d1 and d2, and they are separated by a distance d. Look at the origin of z. So, here is z equal to 0 and it increases in this direction. Here z is equal to d, here z is equal to d plus d2, and you have considered a ring like annular space, which is at a distance zeta inwards from the inward in the block 1. So, the limits of zeta is essentially 0 to d1, and that is the extent of the first object. Extent of the second object block 1, the expanse of block 2 is z equal to d to z equal to d plus d2. Okay. And we have considered an annular ring, width is del z, height is the inner radius or inner perimeter is at a distance y, outer perimeter is at a distance y plus delta y, and here is a shortened or a miniaturized version of the picture. Now, we calculate the volume of the ring element dV, which is 2 pi y del y into del zeta. You can find that out easily. So, this is 2 pi y is the perimeter into del y, it talks about this face multiplied by the width del zeta. So, this is the volume. So, number of molecules present in unit volume of any material, this is 11th standard science, is equal to numbers, I am doing it in the simplest possible way, divided by volume, which you can convert to numbers per mole into mole per mass into mass per volume. So, this is nothing but Avogadro's number. Mass per mole is essentially the molecular weight. So, if we are talking about material 1 or material A or whatever, and volume per mass per volume is nothing but density. So, number of molecules present is in this ring element is, this is per number of molecules present per unit volume. So, you just multiply this along with this volume of the ring. So, that turns out to be rho 1 Na by m1, I will change this to 1, multiplied by 2 pi y dy d eta. Now, we know that the interaction or the attractive interaction between two molecules is beta into x to the power minus 6. So, here the separation distance we have considered is x. So, any molecule we consider which belongs to this ring is at a separation distance of x. So, the potential energy of interaction between this molecule, this particular molecule, and any molecule present in this ring is I will write it down without using any symbol. Between the specific molecule of 2 and any molecule present in the ring is rho 1 minus beta 1 2 divided by x to the power 6. Okay. So, beta 1 2 is the material specific property we talked about. Since we have two materials over here 1 and 2, therefore, we have used the suffix beta 1 2. Therefore, total interaction of all molecules, total interaction of all molecules in the ring element with a single molecule of 2 z distance z from surface of 1 is given as zeta. We have already identified the extent of zeta is from extent of 1 or the expanse of 1 is from zeta equal to 0 to d 1. So, we integrate between zeta equal to 0 to zeta equal to d 1. Y varies from. So, what we assume that both the objects sort of stretch to infinity in this direction. So, y varies from 0 to infinity, and the integral is on minus beta 1 2 divided by x to the power 6 into rho 1 in a m 1 into 2 pi y del y del zeta. Now, what we have from, so this is the expression of the total energy of interaction, the potential energy of all molecules present in the ring element with a single molecule of 2 residing at a distance z. So, this is all molecules. I am a little sorry, this is not the total energy of interaction of all molecules present in the ring element, but total energy of interaction present in of all molecules present in block 1. That is why we do the integral. So, the inner product, this is what is the potential energy of interaction between the specific molecule 2 and all molecules present within the ring element. That is why you multiply with the volume. So, if you do not multiply with the volume, the specific interaction between one molecule over here and one molecule in the ring element is given by minus beta 1 2 by x to the power 6, where x is the separation distance. You multiply it by the total number of molecules present within the ring. So, that is the expression which gives you the total potential energy of interaction between the specific molecule you are talking over here and all molecules, I am a little sorry, I just messed up a little bit, all molecules within the ring is given by this, and therefore, the total potential energy of interaction of all molecules present in the block 1 with a single molecule of 2 residing at a distance z from the surface of 1, that is this particular molecule, is you do the integration in terms of y and eta for the entire expanse of the block 1, and this is the expression. So, we now have to perform this integral. What we have, looking at again at the geometry, is that we have x square from Pythagoras theorem is z plus eta whole square plus y square. This you can write, because the way we have defined our coordinate system, this is the boundary of 1, this is the boundary of 2, this is d, and this distance is z, this is eta, this is y, this is x. Okay. So, we have from Pythagoras theorem, and this is here where you have the ring, it is del zeta, and from Pythagoras theorem you have this. Therefore, so if we mark this as the phi double dash, so phi double dash turns out to be all these are constants. The minus sign originates from the fact that we are talking about the attractive part of van der Waals interaction, which is always negative. So, the interaction itself contains this minus term, minus beta 1 2 divided by x to the power 6. So, you can see that other than y dy dz, everything else, this as well as beta, they are all constants, and therefore, they have been taken out of the integral, and the integral is now reduces to this form. And which turns out to be, if you do the first integration, or let us break it up without, if you look only at this integral, it turns out to be 1/4 of you are encouraged to try it out. Therefore, the overall integral now takes the shape of using the results of this. What you get is this is now 1/4 integrating between eta equal to 0 okay. So, this is what you get. So, this is the integral. So, the potential energy of interaction between one single molecule of block 2 residing at a distance z from the surface, and all the molecules present within the block 1, which sort of stretches up to infinity in this particular direction. So, beta 1 2 we have already mentioned. It is the coefficient which determines the strength of van der Waals interaction and is a material dependent property. Now, the number of molecules per unit volume of material 2 is of course rho 2 Na by m2. Now, we consider a thin strip of material 2 of width delta z, which contains the molecule we have been talking about. Therefore, the number of molecules present within this thin strip is rho 2 Na m2 into A, where A is the cross sectional area, okay, which is this cross sectional area perpendicular to the direction of this. So, the total energy of interaction, so the total between all the molecules present in this shaded zone with all the molecules of block 1 is phi double dash, which is the expression we have obtained for interaction of one specific molecule we have talked about with all the molecules present in block 1. So, now we have to look into, we consider all the molecules present within this shaded region. So, it is phi multiplied by rho 2 Na by m2 to A dz. So, this is the number of molecules that is present, because the volume of the element is A dz, which is present in the thin strip. Therefore, the total potential energy of interaction, now if we calculate it is the total potential energy of interaction between all the molecules of one with all the molecules of block 2 due to attractive interaction is given as GLW equal to that is the expanse of the block 2 as we have already identified. So, expanse of 2 is in terms of z is equal to d to z is equal to d plus d 2, and so this turns out to be minus rho one rho 2 in a square pi square beta 1 2 divided by m1 m2 into I have a 6 over here, this is pi 1 by z cube minus 1 by z plus d whole cube dz. Okay, so this is phi double dash, the expression of that we have multiplied by the number of molecules present within this thin strip. So, you see this rho 1 was there. So, this gets multiplied by rho 2 as well. So, rho 1 rho 2 Na was here, Na comes from here as well. So, you have Na square, you had a pi over here. So, it is sitting this pi, you had beta 1 2. So, the beta 1 2 is also there. You had a sorry, I just missed out this multiplier 6, yeah, because you have a 12 over here performing the integral, and you had a 2 in the prefactor, numerical prefactor. So, overall the expression is 6. Just get it corrected, I just missed this 6 out, and this so the 6 also comes in, and you are left with this particular integral. So, if you now do the integration, you are left with before we do the integral, let us define A12, which takes care of all the constants essentially, rho 1 rho 2 pi square Na square beta 1 2 divided by m1 m2, and this is what is known as the Hamaker constant. Okay. This is the Hamaker constant between material A and 2, between 1 and 2. So, this is a material dependent constant. Property of which depends on bulk properties of materials. Both the materials as well as the nature of interaction at the molecular level. You can see the bulk properties that affect is the, so we talk about the bulk property, which is rho 1, rho 2 and the molecular weights, or the rho 1 and rho 2. The molecular weights are coming in as function or affects the functionality, as well as beta 1 2, which takes care about the nature of interaction at the molecular level. So, this is Hamaker constant. So, if you replace the expression of Hamaker constant in this integral, what happens is you have a pi square over there. So, a pi comes in the denominator. So, your expression for GLW now reduces to 6 pi into 1 by and if you now perform the integral, what you will find is that it sort of turns out to be this will be d 1, I am sorry. Yeah, this is d 1. So, be careful, this is d 1 square. Yeah, just get it corrected, we missed out this d 1 and yeah. So, if you do that integral, it will be so, the final expression for GLW is minus a 1 2 Okay. So, this is the energy of interaction due to between the two surfaces. Okay. So, this is 1, this is 2, and so the potential energy of interaction this is the potential energy of interaction between the two surfaces, considering the attractive van der Waals interaction. Okay. Potential energy of interaction interaction. Okay. So, now you see that it depends, this potential energy of interaction depends on several parameters, that is the separation distance as well as the finite size of these two blocks. So, couple of things you can see immediately from the expression, that is firstly we go on telling, we have been talking that this interaction or this van der Waals interaction sort of becomes tends to 0 as the separation distance increases. We argued particularly if you now compare or try to remember what we had talked about while talking about the atomic force microscope, its approach and withdrawal, that when the separation distances are very, very far. So, this is your tip and this is where your scanning surface is. There is no effective interaction between these two due to van der Waals forces. Well, what would that mean? That would essentially mean that you set d tending to infinity. The separation distance between the two is 0. And now, if you substitute d tending to infinity. So, please do not forget what is d. D is the sort of the separation distance between the two surfaces. The moment you substitute d is equal to infinity in the expression for GW, GLW, let us say we mark that as equation 1, you find that d is there in the denominator of all the terms. So, for the first case is for d tending to infinity, GLW tends to 0. So, there is no van der Waals driven force when the separation distance is very, very high. The second thing that you may want to find out, if that we are talking about the interaction between two semi-infinite blocks, let us say. So, what would be the condition for semi-infinite blocks? The condition would be d1 tending to infinity and d2 tending to infinity. So, this is the condition for semi-infinite block, and then in that case you can see that GLW is minus A12 divided by 12 pi d square. Okay, because d1 and d2 either of them are present in all the other three terms in the denominator. So, for d1 tending to infinity and for d2 tending to infinity, all these terms tends to 0, and therefore, this is the potential energy of interaction. Now, if we consider if we would like to find out the change in the force when the two surfaces are brought to contact from initially infinite separation distance. So, let us say we talk about two semi-infinite blocks which are initially at infinite separation and then they are brought in contact. So, based on the discussion we have already had, we understand that these two are brought in contact. This corresponds to d equal to d0. Therefore, we are talking about the change in the potential energy. So, we are talking about the delta GLW, which corresponds to the final GLW at contact, and the initial one was d tending to infinity, and this gives you the delta GLW is minus A12 divided by 12 pi d0 square. Now, incidentally, if you remember, so these are the two blocks and now these two are in contact. So, this is also a situation where in one of our earlier lectures we have identified that this delta G LW can be represented as gamma 12 LW minus gamma 1 LW plus gamma 2 LW. This is the energy per unit area, of course. Okay. Therefore, what we can get is that we can now correlate A12 in terms of 12 pi d0 square by gamma 1 2 Lw minus gamma 1 Lw minus gamma 2 Lw. So, the biggest advantage now is that the expression of A12 which we had was in terms of beta 12. Other parameters are all known, Avogadro's number, density and the molecular weights are all known, but this beta 12 which sort of was signifying or was representing the strength of van der Waals interaction was sort of a parameter which has to be experimentally determined or maybe spectroscopically, and determination of this parameter is slightly difficult. Now, in contrast, now you have an expression for A12 which is in terms of parameters which can be macroscopically measured, because we have talked in while talking about the different components of surface tension that the different individual components of surface tension can be easily found out, or interfacial tension can be found out using contact angle goniometry using appropriate probing liquids. The only thing that still cannot be physically determined and you have to rely on some model is this D0. Once you have and it's in many cases there are some standard numbers which are available. So, if you have D0 now, depending on the values of gamma 1, gamma 2 and gamma 1 to their Lw components, you can easily determine the strength of the van der Waals or the effective Hammerker constant. Now, in another special case, in case both 1 and 2 are of same material, then what happens is we essentially get A11 Lw is equal to 0, gamma 11 Lw is equal to 0, gamma 1 Lw is equal to gamma 2 Lw equal to gamma 1 Lw, let us say, or gamma 1 Lw is equal to gamma 2 Lw, and then in that case A12 gets replaced with A11. So, this allows us to get an expression for A11 as 24 pi d0 square gamma 1 Lw. The other important thing is that from this expression of A12 we have minus 12 pi d0 square gamma 1 2 Lw minus gamma 1 Lw minus gamma 2 Lw. We know that for van der Waals, pure van der Waals interaction, gamma 1 2 Lw is always can be represented as gamma 1 Lw minus under root of gamma 2 Lw whole square. So, if you expand that, you get gamma 1 Lw plus gamma 2 Lw minus 2 gamma 1 Lw into gamma 2 Lw. So, if you substitute this back over here now, this whole expression gets substituted back here, one is left with so one gets A12 is equal to minus 12 pi d0 square into gamma 1 Lw plus gamma 2 Lw minus 2 under root gamma 1 Lw gamma 2 Lw minus gamma 1 Lw minus gamma 2 Lw, because of these, this and this. So, these two terms cancels out and you are left with the fact that it is 24 pi d0 square into gamma 1 Lw into gamma 2 Lw, which gives that A12 is always positive. And also considering the fact that the expression of A1 is 24 pi d0 square gamma 1 Lw, similarly the expression of A2 will be 24 pi d0 square gamma 2 Lw, one can get A12 is equal to under root of A11 into A22. We will start our subsequent discussion from this point. Thank you.